All right, in this video, we are talking about SN1 substitution reactions. Let's just go over what does this mean, SN1. So S stands for substitution. The N stands for nucleophilic. And the 1 here means that it is unimolecular. The rate is unimolecular. We'll go through all 3 of these things in this video. So here I've drawn an SN1 reaction using terbutyl chloride in the presence of potassium iodide, acetone, and then it gives you your product, which is this terbutyl iodide. Let's briefly just go over these reactions and reactions in general. We have our starting materials here on the left side. Typically, we write reagents on the top of the reaction. Sometimes you'll find them on the bottom, but typically on the top, and typically you'll see solvents listed here below the reaction. And then we always write our product on the right side. Now you'll notice this isn't balanced actually right now. This is a lot of the ways you'll see organic chemistry. You could also see it where you do have the reaction balanced. And I want to bring this up because organic chemists, as I've said before, are kind of lazy. So many times the most important thing is we're drawing the product we're really trying to get. KCl is a byproduct of this reaction, and it's a salt. And we're not trying to isolate KCl, although it forms, okay? So this is really the product of interest. So many times you won't see this byproduct of the salt. And on an exam, what I have in the blue box is what you would be asked to draw in, okay? So organic chemistry, we typically want to look at that carbon-based molecule we're trying to make. We're trying to go from this alkyl chloride to an alkyl iodide. I want to talk about this Ki, or this potassium iodide. Now, when you see it, it looks neutral, but we know that potassium and iodide here make this ionic bond. Anytime you see potassium or sodium or lithium, okay, we're going to be putting this positive charge on top of them. It's not drawn, but it is there. This is an ionic bond. And then we'll put our negative charge on the group that's bound to it. It looks neutral, but remember, the whole molecule is neutral, but this is ionic. Let's now look at this bottom equation. I've drawn them out here. Here I've shown that I have iodide, okay? We also have potassium, all right? And in the presence of acetone and this terbutyl chloride, we still see that we get our product. I've drawn them out separately with their formal charges because I think it clues us in to what is happening in this reaction. I'd like to go over some terminology for reactions. In this reaction in particular, with this alkyl chloride would be the electrophile. Our iodide here would be the nucleophile. And a little more specifically here about our alkyl chloride. This chloride here is our leaving group. Now, as you can see, this nucleophile has electrons, and this is one of the most important things that you'll continue to use. Nucleophiles are the things that attack. This is how I like to think about it. I think about nucleophile. The way I remember this is nucleophile. Think of a nuclear bomb. These things have electrons. They're not always going to be negatively charged, but this one really identifies with this, having electrons. It's very easy to see. This concept will keep coming up again and again, okay? So I just wanted to highlight these two terms. Let's now look at 3 possibilities for mechanisms for this SN1 reaction, the substitution nucleophilic, but it's also unimolecular, SN1. Okay, let's go over some possible mechanisms. Really, logically, you could think of 3 different ways, okay, to put this together, all right, to get this alkyl iodide as a product. The first one could be that the leaving group leaves, then the nucleophile adds. So I'm just going to write an A here. This is A. Leaving group leaves, and the nucleophile adds. Let me write my A up at the top. So I have my alkyl chloride, all right? I'm just drawing it a little different here. The leaving group leaves, okay? So we're going to get this carbocation. Then the nucleophile attacks. Okay, that's one possibility. The second possibility here is that the nucleophile adds to the carbon, then the leaving group leaves. Let's draw what that looks like. So here's our alkyl chloride. And I have my iodide. And I'm going to say that maybe this adds. You can already hear in my voice that this is likely not going to happen. So the iodide added here to this carbon. So the iodide, let's see, the iodide lost electrons, so it is now neutral. But something on this right side needs to be negative, and that's because we have this negative on the left side. Remember, we're always going to be having a neutral or no change in those charges. We didn't lose electrons to space, right? The electrons are all contained within these 2 molecules. So that means something here needs to be negative. And it looks to me like the group that gained electrons is this carbon right there, and you are correct. So we would actually write a negative charge here on this carbon, and then we would make the leaving group leave. If you're like, yo, Dr. Biles, that looks really weird, I agree. Carbon went through 5 bonds here. Okay, the next logical thing you could think of, and I'm calling them logical because we need to consider all of them so that way it really makes sense why the mechanism that is correct, okay? This is kind of a hypothesis. What could possibly happen? So that's what we're doing right now. The last one, nucleophile adds as the leaving group leaves. I'm going to draw my iodide here, okay? I'm going to draw my alkyl chloride. Now, we could have the nucleophile add as the leaving group leaves. This means this is going to happen at the same time. So I'm going to draw the iodide attacking, okay, while the leaving group is leaving. We're avoiding that carbon with 5 bonds. And so this is actually for SN2. This is actually a mechanism that we will go through in the future here. I can go through here and draw in my chlorines because we do have, see, you've already caught me. I do forget to put in these byproducts because, well, I'm a lazy organic chemist. I'm always most concerned about the carbon group. So we do have a chlorine here at the end, and then this one's also this chlorine that has left. So I apologize, I missed that. Let's make them the same color here. So these are the 3 possible mechanisms. There, now everything looks pretty. That we could consider. Now previously we saw that SN1 stands for substitution nucleophilic reaction that is unimolecular. That means that the rate of the reaction is dependent upon only 1 molecule here. So the correct mechanism here is mechanism A. Now, this bottom one, C, does happen under certain circumstances. This is an SN2 reaction, which we will cover soon. Let's talk about the potential energy surface for this reaction. So let's just redraw a reaction here at the very top. So we have our alkyl chloride. And our first step here is formation of this carbocation. This is really slow. So we're going to make this chlorine leave. We're just kind of waiting around until it leaves. And that's because nothing can really happen with this potassium iodide until a more reactive species forms. I'm going to draw I- here. Okay, and then we're going to attack our carbocation. Let me make that red. All right. Now we did also form Cl-, which is just kind of hanging out. It's hanging out with that potassium that's in our solution, all right? And then we're going to end up making our product here. I'm going to draw this reversible, and we'll talk about that in just a second. Okay, let's go over the potential energy diagram here. So we're going to have energy on the left side, and the bottom of these graphs are always the progress of the reaction, or reaction progress. I'll just write, I already started with P, so progress of the reaction. Okay. So we've talked about it being unimolecular. That means only one of these molecules is really in this rate determining step. So we're going to start our reaction with our alkyl chloride, and we have our potassium iodide present. I'm just going to draw out I- actually, because it's really the thing doing the chemistry. Okay, we're going to start our rate nominally. This is a relative rate here, okay, relative energy here, and then we're going to go through a transition state. Transition states are higher in energy, and we cannot isolate them. Now, based on the mechanism that we talked about, we know what this is doing. We know what this first step is. It's very slow. The chlorine leaves, and we make a carbocation. So this next energy level here would be our carbocation. We have our I- still hanging out. It hasn't done anything yet in the reaction. And we have our Cl- because it left. All right. Potassium is present in each of these steps, so I just haven't put it in here because it doesn't change the energy. It's still K+ for the whole thing. So it's nominally not important. All right, so after this step, this is when the iodine adds to the carbocation. It kind of makes sense that this carbocation here is higher in energy than our starting material, which is down there. And that's because we know carbocations are higher in energy. It's got this empty p orbital. This carbon isn't very happy. Carbon wants to have 4 bonds. That's why it's higher in energy. The next step doesn't require as much energy. It'll be lower than that transition state, that higher energy that is over here. Okay, so now it's going to go through the next step of the reaction, and we're going to form our product. We've added our I- here, and then we have our Cl-. So there, we have our product. The rate of this reaction is dependent upon only the formation of the carbocation. And this is because this is the highest energy step here. So this energy difference here, this is determining the rate. Okay? So this delta G double dagger is another way that we would say this. So, okay. Now, SN1 is dependent only on this substrate. SN1 is unimolecular. It's only dependent on one reactant. Okay, not I minus. It has nothing to do, it does not care how good of a nucleophile that I minus is. That could get us into another type of reaction. Now, the other thing I want to highlight here is Hammond's postulate. Hammond's postulate just states that this transition state is going to look very similar to our intermediate that's right beside it. And this is important because this is going to help us understand what the transition state looks like. So let's write this out. So the transition state, this is a nice way to think about this. Transition states, I'm just going to say mirror intermediates closest to them. So when we think about this, which intermediates are closest to the transition state? Well, that would be this intermediate here. So our transition state really looks similar to a carbocation. So, and that's exactly true. So our transition state looks like the following. Partial positive on the carbon and a partial negative here. So here's our transition state that's looking closer to that carbocation. It's because the energy here of this intermediate is closest to this transition state. So that gives us a clue about what the transition state looks like. So that's kind of the first thing. What does the transition state look like? So I'm going to write, what does TS look like? And the second thing that this Hammond's postulate tells us is really how to make the reaction go faster. And you're like, whoa, in this little postulate, it's not little, it's super cool. All right, so let's think about this. If the transition state looks like the carbocation and it mirrors this, the energy of the transition state is very near this intermediate, okay? If the energies are similar, if I was able to do this, if you can lower or stabilize then the reaction goes faster. That's kind of the neat thing about Hammond's postulate, in that because the transition state mirrors the intermediate, if you can stabilize your intermediate, the transition state will also come down in energy. And that's because the energy of the transition state is mirroring what the intermediate looks like because it looks really similar. So if I can stabilize the intermediate, this carbocation, which we know some about actually, then that means that the reaction will go faster, okay? So I'm going to write the following. So the second thing Hammond's postulate tells you is like how to make the reaction go faster. So the more stable the intermediates, the faster the reaction. Okay, cool. Let's go through some kind of requirements for SN1 reactions. You need to have a good leaving group. And we saw that in our first example there. What are good leaving groups? Well, good leaving groups Our conjugate bases of strong acids. These strong acids with pKa values of typically less than or equal to 0. Okay, so let's write some out. What are good leaving groups? Let's give some examples here. So Cl- was in our previous example. Cool. All right. Br- is a great leaving group. I-, then we have tosylate. Tosylate looks like the following. It is a sulfonate derivative here. This TS stands for tosylate, so I'm going to write this out. Tosylate. This tosyl group is this toluene derivative. It's a benzene ring with a methyl coming off it in the para position to your sulfonyl group there. And then we also have a mesylate group, OMS. So a mesylate group is also a great leaving group. And it looks like this. This Me for a methyl here. And you can also have a triflate, which we won't see as often. You can also have a triflate group. So this OTF is called a triflate. Now it sounds like I'm making up words. This is a real thing. And so very similar in structure here. These look like sulfuric acid derivatives, and that's exactly what they are. And this one, it just has a CF3. This one's a really good leaving group. These leaving groups are very stable as their anion. Okay, remember that strong acids, when we deprotonate them, their conjugate bases are fairly stable. They like having the negative charge. That's what made them a strong acid in the first place. Strong acids give off protons, and they're pretty happy to do so. So this is where our pKa and acidity kind of comes back in. Now, two other leaving groups that are also really great are the following. So you can have water as a good leaving group or an alcohol as a good leaving group. Now, water or an alcohol could also be a great leaving group. However, I just want to caution you, I'm not talking about, let's say if we have tert-butanol, I'm not talking about this leaving. Let me draw my equilibrium arrow just equal. You're going to quickly see that this is actually not equivalent on both sides. Here, by doing this, you make this really strong base. And this is a really strong Lewis acid, so I'm just going to write strong acid. These don't want to form. We don't want to form really strong bases and really strong acids in one. So actually, the way that this goes is not equivalent. It just doesn't form. This just doesn't happen. Okay, now one way that you could do this is if I were to have a protonated, let's say if I have a protonated alcohol, okay? So if I have something like this protonated ethanol is kind of hanging out here, you could imagine that with time, this could come off, and this does in fact happen. And that's because you're making this neutral alcohol here, okay, which has a conjugate, which has a pKa of around 15, okay? So this is okay being as itself. You aren't making both a strong acid and strong base. You're just making this strong Lewis acid here, strong Lewis acid. All right, so this can happen. But just remember, when you make it leave, it needs to be neutral here for water or alcohol, okay? You're never going to see just OH minus or an O minus popping off and forming a really reactive carbocation. Okay, let's go over more requirements here. The carbon with the leaving group is sp3 hybridized, like we've seen. And a carbocation form must be stabilized. And we've talked about stability of carbocations. We've talked about how if you just have a CH3, okay, just as CH3, this methyl cation, this is much less stable than if you were to have, say, a primary carbocation, which is much less stable than if you have a secondary, okay, which is much less stable than if you were to have a tertiary carbocation. So here's primary, secondary, tertiary. Put a smiley face by the tertiary. That is definitely what we prefer. So these form more readily. So we talked about the reasons of why this tertiary is more stable. So I'm just going to write nope underneath this methyl cation. Just don't form that. It's way high in energy. Not going to happen. This would be really slow. Typically, a primary carbocation is not going to form. We will get into rearrangement soon, okay? This is slow to form, the secondary. And this can form readily, this tertiary. So these sp3 carbons with the leaving group that can form a tertiary carbocation are most likely to do the SN1 reaction. Let's go over one more concept. We've talked about hyperconjugation stabilizing carbocations, and we've also briefly talked about carbocations being stabilized by resonance. So let's just write that out. So we've got hyperconjugation, which is the donation of electron density by adjacent sigma CH bonds. And resonance is the second stabilization fact here. So we've got hyperconjugation and resonance. Resonance can stabilize carbocations. So let's say, for example, I'm going to write a little blue line there. So let's say, for example, we had a benzyl chloride. I could draw this chlorine coming off. Okay, we draw what didn't change. There's the benzene ring. I have a carbon there, and it looks primary. However, we know, because we have practiced lots of resonance, that this carbocation, this positive charge, is not being carried only by that carbon. It's shared, okay? So this is showing that that carbocation is shared within the molecule, and that lonely carbon that I'll put a little red circle on, although it looks primary, it is benzylic. And so this carbon is not the only one that has to hold that positive charge and be really unstable. This stabilizes it because all of the carbons are helping pitch in with this. All right, and the last requirement here is that the nucleophile is a weak base or non-basic. And what do I mean by that? So the nucleophile should not be something that's a really strong base. So let's go over some examples here. In the first example we showed, we had I minus. Let's go over other examples. Water can act as a nucleophile. You can also have some kind of an alcohol here. Now, when I say R, just typically means an sp3 carbon or something. So think something like ethanol, okay? We can also have Cl minus as a nucleophile. It is a weak base. Br minus can be a nucleophile, and I minus can be a nucleophile. Let's write a few more. You could have a thiol, or SH, okay? You can also have an azide. This is a fun compound here. Now, ones that are not good nucleophiles for SN1 are the following. Hydroxide. You can have an alkoxide. You can have a thiolate, this S minus. Actually, amines are not good for SN1. You can also have a cyanide anion here. Now, these are all too basic for not that kind of basic, but for SN1 reactions. Instead, remember that typically we're making this pretty stable carbocation. These are really strong Lewis acids. They are not compatible with really strong bases, okay? Instead, these strong bases are useful for another type of reaction. That we'll get into. This is for E2, okay? So strong Lewis acids are incompatible with basic or moderately basic nucleophiles. So in general, something just to remember is that nucleophiles that have conjugate pKa's, or their conjugate acid, the pKa of their conjugate acid, if it's more than 10 or equal to 10, they're really not compatible for SN1. Let me draw that out a little better. So we won't be using SN1 if that nucleophile has a conjugate pKa of greater than 10. Let's do a little practice problem. All right. So let's take the following example here. I'm going to combine some of what we learned with stereochemistry. Let's say I have the following molecule. This alkyl chloride. Now, as it stands, if I were to run this reaction in the presence of Ki and with a solvent of acetone, we know the starting material doesn't have a chiral center, okay? We know we're going through a carbocation transition state. That means that the iodide can add on either side. And you're probably like, yo, we don't need to draw both of these. These are the same molecule, okay? These are the same. So on your paper, you could just draw one, because there's no chiral center. So just draw one, or you could just draw it all flat, and that also indicates you know that there's no chiral center. It doesn't matter if the iodine or the methyl is wedged or dashed. These two are the same, okay? Now let's do an example here where it's not the same. So I've got my chlorine. We know that that's the leaving group, okay? And let's add some spinach on this left side here. This would mean that we do have a chiral center. We have one chiral center. And it is right here, Okay, so you can go through your Kahn-Ingold-Prelog rules here to figure out if this is R or S. So let's just do this together. We've got 1 being the chlorine highest atomic number, 2 would be this left side, okay, and 3 would be this side here, the cyclohexane ring, and then 4 would be back. Cool, 4 is back. So if we look at this, we can use our left hand, use your left hand, curl from 1 to 2 to 3, okay? Your left hand works, your thumb is where the 4 is at. Cool. So we have an S stereocenter here. Now, if I draw this, and I say I'm in the presence of Ki, an acetone, by drawing this molecule, I'm saying this is the one that I have. I have the S enantiomer. This is the one I'm using in my reaction. Sometimes professors will write the words optically active underneath. Typically, I will just draw it as is and want you to identify that, hey, that is chiral, okay? So optically active could be drawn underneath, though. Sometimes I'll add this in. Either one, I'm saying here that the S is the one we're looking at. When it's optically active, we talked about how this rotates light. And that means that the S enantiomer is in excess, okay? This is the one that predominates. So when we draw our product from this, we don't get just one product. Remember, we're going through a transition state here, and then we make this intermediate that's a carbocation. And that carbocation can be added from the top or the bottom. So the carbon I've circled in green is the one that's going to change. It's good to think about the mechanism because it helps you understand what didn't change. So none of this changed. The cyclohexane ring is still there. The dimethyl is still there. And we know that we have iodine on either side. That means we have both the R and the S enantiomer. So the answer that you would want to write is this product, just one of the enantiomers, and racemic, okay? Now, you could also draw both of them. So this would be the S enantiomer. You could, on an exam, draw both. Again, notice I'm not even writing KCl. Notice how that's dropped off already. We're really focused on the carbon-based product that really is doing the chemistry that we're interested in, okay? On an exam, you could draw both of your enantiomers, okay? So let's just circle what you can do. So you can either, let's see, this would be the R enantiomer. So you could draw this as your product. That would work. Okay? Or you could just draw this as your product. And this indicates, by just writing one of the enantiomers, writing racemic, this indicates that you have both present. Okay, well, that is it for this video about SN1 reactions. Next week, we're going to be focusing on SN2, and then we're going to start to get into elimination reactions. This is just the beginning. This is really the meat and potatoes of this course. There's so many fundamentals in organic chemistry that we learn with these reactions, all right? That's it for this video. I will see you in the next video, and have an awesome weekend.